This video will describe black holes, some of their characteristics, and also describe the evidence that makes us confident that black holes actually exist. So some questions for you. We have some experience with the life history of stars at this point in the course that I instruct. So what happens if the mass of a neutron star goes beyond 3 solar masses? The neutron star has degenerate gas pressure inside, but there's a theoretical limit, 3 solar masses, and if mass gets above that, gravity wins, and there's no future degenerate gas pressure of any type that can prevent the mass from collapsing down to a point, and we have the formation of black hole. Black holes appear in science fiction, and they have justification. This is not a situation where the science fiction came up with the idea first, but we have the scientific hypothesis, and supported by evidence, as we'll see later, that black holes exist. They are not just in science fiction. However, how they're treated in science fiction is science fiction. But there's some real facts about black holes that we'll discover here. So again, as I said, gravity wins if we get above the mass value that the degenerate neutron gas pressure can support. So we shrink down to this object called the black hole. This black hole, even though the mass is concentrated down at a point, it has an effect on space, a significant effect, out to something called the event horizon. The event horizon, we'll talk about that a little bit more. But this would be how close you could get to the black hole and still escape, and how close light can be and still escape. So the event horizon, if you go closer to the center of the black hole than the event horizon, it's impossible for light to escape. It's impossible for you to escape. The real reason for that is that the mass has curved space-time in such a way that all paths lead back to the center. You can kind of talk about it in a gravity sense, that escape velocity and trying to escape from the mass of the black hole. And at the event horizon, you need the speed of light to escape. No object can travel as fast as the speed of light. So if light can't escape from the black hole, then nothing can escape. But the real scientific description would be that inside the event horizon, space is warped so much that all the paths lead back to the center of the black hole. So event horizon, Schwarzschild radius is another name for this, where we have a distance that you have to stay away from if you don't want to die inside a black hole. So a little drawing here of black hole and different light paths that have been sent towards the region from the left side, headed towards the right side. And if it's far away, then we get the effect of the curved space-time bending the path of the light. But as this light gets closer, there is a place outside the event horizon where light can actually go into orbit around the black hole. Then we have the event horizon. Here's we have some light crossing this event horizon, and it has some path inside the black hole, but headed down towards the singularity. Black holes have mass and black holes have spin, as they form from an object that's collapsing. And objects that collapse, if they're rotating at all, they're going to spin faster and faster and faster as they collapse. We're not going to discuss the effect of how the spin of a black hole affects space around it. So artist's view here, the black hole will have gravity effect outside it. So there will be objects, if they're headed towards the black hole or the vicinity, they can be affected and go into orbit around it. And the black hole will form a disk of material, just as Saturn's rings have a disk kind of shape. Our spiral galaxies have a disk kind of shape. And when there's rotation, the material in the universe tends to form this kind of pancake shape. So we get what's called an accretion disk here, and you'll see that again in the future. The black hole itself is spherical, and then we have magnetic fields, and we have the situation where there can be light leaving the vicinity of the black hole. It's not leaving from inside the event horizon, it's leaving from the vicinity where there are strong magnetic fields and high temperatures, and that's going to be important in detecting black holes. So the radius of this event horizon, how large is a black hole? If our sun would in the future become a black hole, it does not have a mass to go through the process. But if we have one solar mass in a black black holes can come in all different types of masses. But let's say it's 1 times the mass of the sun. This would put all the mass inside a 3-kilometer radius. So that's around 2 miles. But 1 solar mass. 2 solar masses, the radius gets bigger. And the radius is proportional to the mass. And what my students should know is that if the mass is larger, the radius of this event horizon, the source shield radius, is larger. 500 solar masses, we're still smaller than the Earth. 1,500 kilometers radius for the event horizon. And here's a sketch more from the point of view of warping space-time. This does not show you the shape of the black hole. The black holes are spherical, but shows you the bending of space-time, and this would be the event horizon up here. So general relativity, of course, has to be used in these high mass situations. For large masses, Newton's law of gravity is not correct. It works okay on the Earth. Some corrections are made even for the mass of the Earth, but the real situation getting into the mass that are 1 solar masses and beyond, you really must use Newton's modified, don't use Newton's law, use the modification created by Einstein, the general theory of relativity. And in that theory, mass and energy cause space-time to bend, to shift. Both the space coordinates, x, y, and z, and the time gets altered because of the presence of mass and energy. General relativity is well tested in its various forms, its various predictions, and so far all the experiments are in line with predictions of general relativity. So it's an accepted theory, a fully accepted theory. 1916, Einstein came up with the general theory of relativity, and it's been worked out since that to make various predictions, including black holes. So general relativity is our basis for understanding gravity in high gravity situations. It must be used instead of Newton's laws. So again, the confirmation for this came in 1919. If we have, again, a picture here of warped space-time, and we're sending light on these red paths in the vicinity of the sun, the direction to the light source is bent, is changed from a straight line. So in 1919, photographs were made of a solar eclipse, and this is a negative view, so this is the dark moon here, but we have stars appearing, locations of stars on the sky, and the positions were noted, and the shift of the positions of the stars was as predicted by Einstein's theory of general relativity. So there is confirmation in many ways. Time dilation part of the general theory of relativity: if gravity is stronger, time runs more slowly, and this is part of the calculations used for the GPS satellite system. It is an important effect that must be taken into account. The Earth's gravity causes the clocks to run at a rate different than if there was no gravity present. And if we would be sending a clock towards a black hole, what we would observe is the clock would run slower and slower and slower as it got closer and closer and closer to the event horizon. And in fact, the clock would stop at the event horizon. It would be very difficult to see because at the event horizon, light that comes back towards us is strongly gravitationally redshifted. It's not a Doppler shift, but the light loses energy as it's leaving from a region close to the event horizon. So time does slow down. If someone goes into a black hole, we would not see them go in because they're motion would stop at the event horizon from our point of view. The person actually would go on in, and they would carry a clock with them, and it would run until it was stretched to spaghetti type of clock, and those atoms didn't work, and the person's not going to be able to detect those atoms. So yeah, I'm going to pause the video a little bit and think of some questions that you would ask your instructor. Okay, evidence that there are black holes. And the primary evidence comes from the fact that gravity still exists. Light cannot get out of a black hole, but the effect of gravity is still in force around the vicinity of the black hole, outside the black hole. When the mass goes into the black hole, it doesn't disappear from the universe. It's still there, and we get this gravitational effect for things around the black hole. This especially is important when the black hole is in a binary star system, where the black hole is there, and then a star that gives off light, that we can detect its motion, and enables us to measure the masses of the object in the system. So the binary star system, we have X-rays coming from these systems with the black hole present as the star in the system goes into its giant phase and the atmosphere of the star swells up. There will be the opportunity for the mass from that atmosphere to move over, headed towards the black hole. As it falls towards the black hole, it speeds up with that high gravity situation. There are collisions in the material, and it gets to a high temperature. This accretion disk, as material falls towards the black hole, it falls into this kind of pancake shape accretion disk. The atoms are colliding, there's high temperature, and at this high temperature, the disk emits X-rays. We see light from the regular star, this giant star, and its Doppler shift can be recorded for this regular star. Its orbit can be mapped out, and we can calculate what the mass is for the star that we see and the star that we don't see. That star that we don't see is above 3 solar masses, 5 or 10 solar masses, but not emitting regular visible light like normal stars do, but instead X-rays coming from this binary star system. So this is the evidence of black holes around stars scattered throughout the galaxy. When in a binary star system the masses are determined and there is an object that is not emitting visible light that has a mass of greater than 3 solar masses. Well, it can't be a neutron star. It's greater than 3 solar masses, so the interpretation is it's a black hole. We do not see black holes directly. There's no light that comes out of the black hole, but we can detect light, radiation, X-rays, form of light coming from the region around the black hole. So here would be an artist's drawing on the right side and a photograph of the sky over on the left. Cygnus, constellation of Cygnus, a summer constellation. And the interpretation is that there's a giant star in that system that is shedding mass. Mass is falling towards the black hole. And we get the accretion disk here. There's strong magnetic fields, so we get kind of a beaming of radiation that can take place. There we go. Now, I'm not going to go to this in this video, but there's a little interesting video of a black hole in a binary star system. Again, it's animated. It's not real photography. But go to YouTube, search for Mark Garlick, and search for black hole, and you would find this video. So we're going to move on. But here I am going to let you see an animation. These are real star positions. These are real star positions that have been mapped out in the Keck telescope in Hawaii. And from, if you look here, 1995, July, time goes forward. These stars are changing position. Like it goes through 2010. Especially note the yellow loop here. This star completes one orbit in this time. This is a fairly large distance here. How is it that this star in this yellow orbit is able to complete the full orbit? 1995 to 2010, 15 years. It's moving at high speed. And it's moving at high speed because of the large gravity at the center of the Milky Way galaxy. it's estimated that there's an object that has 4 million times the mass of the sun. It's not giving off visible light. It's too massive for a star in any case. But this is evidence that there's a very massive black hole at the center of our galaxy, the center of the Milky Way galaxy. As astronomers studies the motion of these stars that are near the center of the Milky Way galaxy, they find that they're in orbit around a very massive object. The way that the orbit's shape is, the speed of the stars in the orbit, gives indication that there's a supermassive black hole at the center of the Milky Way galaxy. And astronomers have looked at many galaxies now and have come up with the conclusion that having a supermassive black hole at the center of the galaxy is the normal case. Galaxies all contain supermassive black holes, at least if they're a regular galaxy. If they're not just a small irregular galaxy, but even those may have black holes. I may not just be reading the latest information, but it's a regular thing to have supermassive black holes at the center of galaxies. The motions of gas and stars at the center of other galaxies can be detected, and there's indication that there's a huge mass at the center of these galaxies, black holes. So here's a photograph over on the right side of a different galaxy, not the Milky Way, but showing a disk of material around the black hole. And again, we're not seeing the black hole directly, but we're seeing energy emitted from the region around the black hole. And then there are jets of gas being launched off of the north and south magnetic poles of the black hole. So again, more evidence of these very massive objects. So if you wanted to go to black hole, any precautions need to be taken? A lot. This accretion disk is very hot, sending out tremendous amount of X-rays. There are large tidal forces near the black hole. This is a huge object. And the moon creates tides for our oceans. The tides are much more severe near the black hole. And as you would go towards the black hole, if it's a reasonably sized, you don't get killed right away. You get inside the event horizon before you are stretched out, made into kind of a tube of spaghetti. It's been called by Stephen Hawking and others. And so you die because your biological systems are not supported, and then all your mass goes towards the center of the black hole. You never get out if you get inside the event horizon. So it's an imagination thing. There are no black holes near us. I think the closest one is about 1,600 light years away. So it's interesting to think about. It's not a danger that you're going to face in your lifetime. Another video that I'm not going to go to, but you could do a search for 60 symbols and black hole and the size, and the person there does some calculations for you on the size of the event horizon, the source field radius, and again reviews some of the evidence for black holes. So it's worth your viewing. Again, write down questions and ask your instructor. Black holes, the final stage in the life of a very massive star. Stars the mass of the sun will not form black holes, they'll form white dwarfs. But the very massive stars, as they go through their supernova explosion, if there's more mass than 3 times the mass of the sun in the object at the center, it won't be a neutron star, it'll be a black hole. So keep reading, asking questions.